Yeah, good afternoon. Today I want to discuss about machine learning. In that, one of the concept is computational learning problem. So before going to the topic, just I want to explain about what is a computational problem, learning problem. Here in this, actually, we have to predict the values in this. So suppose if COVID patients are there, so we are taking some data sets of the COVID patients. If we have proper data sets, then we are going to get the proper results of that. Okay, suppose if we take 100 samples of the COVID patients, okay, who are affected with the COVID, and if you are not training the machine with the proper prediction, what happens here is so 100 data sets we are giving to the machine, it will predict that and it will show only the 50 members are affected with the COVID. Why? Because the prediction has been not done properly and the machine has been not trained the data set properly. Okay. So here it shows only the 50 members are affected with the COVID. So for this, I want to share you a PPT. In this, I will explain you briefly about how we are going to discuss about the computational learning problem. So here in the computational learning problem, to understand, okay, to understand what kind of tasks and are learnable, what kind of data is required for the learnability. So if we are training the machine with the different data sets, what happens here is if we are training the data with proper data sets, the machine will predict that and will give the proper results, and we are going to get the accurate output for that. Okay. Suppose if we are if we are training the machine with the 100 members data we are collecting and we are training the machine properly and we will get the output 100% accuracy we are going to get. If we are not training the data, what happens here is we are not going to get the output properly. 100 members, we are taking the data. So from that, it will predict only the 50 members are affected with the COVID and 50 members are not affected with the COVID. So it is not correct. 100 members are affected with the COVID. So it will take the samples of that. It will predict that and will show that these members are affected. Suppose if we are taking only the samples of 50 members, we don't know exactly how many are affected with the COVID in that. So here in this, we have the graphical representation in the computational learning theory. So here it will show that it will predict that plus. This all comes under the positive and minus. This all comes under the negative. Since plus these all are the affected with this all are affected with the COVID and this all minus these all are not affected with the COVID. Okay. So we has some prediction and here in this we have error. Okay. How errors will occur if we are not training the data sets properly. Here we are going to say in this computational learning theory to understand the kind of tasks are learnable, what kind of data is required for the learnability and what are the space time requirement for the learning algorithm. Okay. Here to develop an analysis model, develop algorithm that probably meets desired criteria, provides guarantees for the successful algorithm. So here in this, if we do the prediction properly, then we are going to get the proper data sets. For example, here also I want to discuss about the multiple multi-recommender system. So suppose if you are training the machine with very well, so when you're buying any product in the Amazon, so directly when you're buying a product, it will show the pop-up in your WhatsApp and your Gmail and in your Facebook. So there you are going to get that which of the mobile you have to that related. So example, if you're buying a mobile in that, so it will recommended you that the machine will recommended you to buy the pouch of that screen guard, okay, and Bluetooth for that, etc. and etc. This all comes under here, okay. It will recommended the machine, okay. The machine will recommended us according to the whatever we required. So we call it as a multimodal recommended system. Even though suppose if your example, if you're training the data sets very well in the machine, here it will predict that. How it will predict? Here in the case of prediction, here you can see that. So suppose you are listening in melody songs, you are interested in melody songs. Okay, you are interested in melody songs. So the machine will daily, if you are listening a melody song, the machine will recommend you one of the best melody songs for you. Why? Because every day you are listening that songs, the machine itself identify that and you are interested in melody songs and the machine will recommend you to listen the melody songs. So here you can see that to develop and analyze a model, develop algorithm that probably meets the desired criteria, proves the guarantees for the successful algorithm. So then using this all successful algorithm, then we are going to predict that, and then we are going to get the results of that. So what tasks are learnable in order to learn? What type of data is required, and should be size of data, resource requirement, space and time, develop algorithm under the criteria, prove guarantees. So here in this, we call it as a PAC. So PAC is probability. So here you can see that is probability approximately correct. We call it as a probability approximately correct in the computational learning theorem. So here we call it as a PAC. PAC is nothing but the probability approximately correct hypothesis. So here what we mean by an hypothesis? Hypothesis is the imagination in future example, if you want to, or if you're designing any robotic machine, okay, just you take it as a robotic machine you want to design, some touch screen mobiles you want to design now. So here in future what we are going to, in that example, if you are doing only 5 to 6, just you are going to develop, now you are developing that, and in future what are going to be existing. So that comes under the hypothesis, just it is an imagination. We call hypothesis is nothing but the imagination. In the whole universe we have many devices. In that what we are doing here is just we are planning to implement, and we have to show in the existing. So only if you are there in the existing. So here you can see that probability learning and approximately correct hypothesis. A good learner will learn with high probability and close approximately to the target concept. With high probability, the selected hypothesis out to the lower error. So here already we know the probability of that. So here P of A by B equal to P of B by A into P of A by P of B. So this is the formula for the probability. So here we call as approximately correct with the parameters. So here we can see the epsilon and the delta. PAC learning requires small parameters, epsilon and the data with the probability at least uh, 1 minus lambda. A system learn the concept with the error. So here you can see the epsilon is upper bound on the error is accurate. The hypothesis with error less than epsilon. So accurate 1 minus epsilon. So here you can see that delta gives the probability of failure in achieving this accuracy. So here we can see in this example. So here I will show you one example in this, how exactly this probably, how we can say that exactly it is probably correct. So here I have one example, that example a n number of car having prices and the engine power and the training set, we call it as PE. Okay, P is nothing but the price, and the E is nothing but, and E is an engine for the car, is a family car or not. So here in the example we are finding that just we are taking the example as we are showing that whether it is a family car or not. So this we have to show into the graphical representation. So how we are going to show in the graphical representation is, so here n number of cars having price and the engine power as training set, find the car is a family car or not. An algorithm gives the answer whether the car is family car or not. So it will find out in the graphical representation, that it will show that whether it is a family car or not. So it will predict how many this is family car, what are the requirements we need, and whatever we are examples we are giving to the machine, it will show that, it will predict that, and it will show that it is a family car or not. C is the target function. Instance within the rectangle represents the family car outside and not a family car. Hypothesis H closely approximately C, and there may be error region. So here in this, you can see that. So here in this, we have, this is the price of the car. And here we are showing that in the graphical representation that it is a family car or not. So here, this is the error. So here you can, so here you can see this. Okay, this is the price of that okay, family car, and this is the engine size. So here this all comes under the family car, so which is plus plus plus. Okay, this all comes under the family cars, and which is minus outside, so it is known as an not a family car. So it represents that it is a family car. Okay, so which is which is inside of this plus plus we call it as a family car, and outside we call it as a not a family car. Suppose if example in this only I will explain you that, So suppose if you are predicting that, if you are taking the samples of dead samples, whether the patient is affected with the dengue fever or not, just you are taking the blood samples. If 70 members of they have given their blood samples, so here the machine will predict that. So example, in 70, if 50 members are affected with the dengue fever, and 20 members are not affected with the dengue fever. So here you can see that this all plus comes under the dengue fever. So they are affected with that. And here minus, these all are not affected. So which is this we have to check. Okay, accordingly, then the machine, what are the data sets we are training the machine will predict that and it will show the results accordingly. Okay. So this is called, in this week, this is called as a price, and this is an engine. Here we can say that this is a family car and this is not a family car. Okay, here in also you can see that outside the boxes, this all considered not a family car. So what is our question here? Your question is, we are taking the sample or example of, we have to show that whether it is a family car or not. Here in this, we are showing that all the plus comes under the family car and all minus comes under the not a family car. Okay. So here you can see the C is the target function. Okay, so the C is the target function, and represents the hypothesis. Hypothesis, already I said that the hypothesis is nothing but the imagination. In the imagination in the whole universe, we are taking many things are there. We are taking only the few examples which are going to be existing in the future. Okay, not all. Example, of we are taking a H1, H2, this all comes under the, okay, that we are going to exist in the future. So okay, like example, we have driverless cars, okay, that we call an H1, and we have robotic teachers that we call an H2, next to H3, and touch screen of the mobile. Okay, okay. So different technologies we are going to implement, and just we are imagining now, just we are in future enhancement, we are going to develop that. Okay, so that we called it as an hypothesis, imagination, future, what we are going to implement, that we call as an hypothesis. Okay, so here we have false positive and false negative. For instance, lights on shaded regions are false positive, okay, according to, and negative according, or actually function C, but these are negative positive based on the hypothesis H. Hence it is called a false negative and false positive. So here you can see this, which is touching in the, so already I said that we have what is our question here? We have to find out whether it is a family car or not. So how we are doing the prediction here? In this, we are doing the prediction that, so this all comes under, so this shaded region, this all comes under the false negative. False negative, how we have to find out the false negative? C of X is equal to 1. This is a family car. Okay. H of X is equal to 0, not a family car. So 1 represents as a family car. Okay. And 0 represents as a not a family car. So we call it as a false negative. So whenever the shaded region is there like this positive is nothing but a family car, and this all shaded regions is known as a not a family car. Okay, here we have all minus. This all comes under the not a family cars. Again, I will show you false positive. In this, we have two types. So one is false positive and false negative and false positive. So here we have totally reverse of this. So here we took C of X is equal to 1, H of X is equal to 0, right? So here what we are doing now, the false positive. So in this false positive, C of X is equal to 0, H of X is equal to 1. So here it is totally reverse of that, false negative and false positive. So whenever we have a C of X is equal to family car, H of X is equal to 0, it is not a family car. So here you can see in the false positive, C of X is equal to 0 and H of X is equal to 1. It is wrongly classified as known as false positive. 1 is a family car and 0 is not a family car. Okay. Again, I will revise once again. False negative and false positive. In this false, we have false negative and false positive. So here we have to show that whether it is a negative or positive. Okay, hence it is called a false positive and false negative and false positive. So here, whenever the shaded region is known as the false negative, sorry, the false negative. So here, the C of X is equal to 1, it is a family car. H of X is equal to 0, it's not a family car. Okay. So here we are doing the prediction. So what is C here? The target function. The target function. Okay. The target function, we call it as an C, and H. What is H here? H is an hypothesis. Okay. And here in the graphical representation, we can see that this all shaded, we have downside, and here in the false negative, we have only the downside, the shaded region. So here in, we can see that up and down, we have the shaded region. So we call it as an false positive. Okay, both sides, if we have, we call it as an false positive. Only we have one side, it is called as a false negative. Okay, here we can see that totally it is reverse of that. The C of x is equal to 0 and h of x is equal to 1. It is wrongly classified and is also known as false positive. One is a family car and zero is not a family car. So in this, so the error region. What is error region here? How to find out the error regions in this? So how, before going to this error region, what you mean by an error region? Error region is nothing but whenever you are not training the data set, training the machine with proper data sets. Okay, the machine will not predict properly whether it will show. Already I said it is not showing either family car, either it is a not a family car. So yeah, so here we can see the error region in this. The probability of an error region being small. The error region P of C, X or H, okay, equal to epsilon. Error region is equal to C, X or H. So here you can see that the shader region, okay, here C is there. C, what do you mean by C? The C is the target function. So what is the target function here? We have to find out whether it is a family car or not. Here, so C and H is the hypothesis of this. Okay. H is the hypothesis of this. So here we have approximately correct. Okay. The hypothesis that approximately correct and the error less than or equal to the epsilon, where we have to find out whether it is lies between the 0 to 0.5. Okay, the probability of approximately correct low generalization error with high probability. Okay, we call this as, okay, this is a formula for that. So this is the approximately correct. Approximately, how we can say that it is approximately correct? So how we have to identify whether it is an approximately correct? If an hypothesis lies between H and C, okay, it is a shaded region, then it is known as an hypothesis correct. So here you can see that this is the target function. Now this is the, okay, epsilon, this is greater than epsilon, okay, HS, okay, hypothesis, this is the hypothesis. So you can, here you can see this HS, main H, capital H means the imagination. Okay, we are imagining. Okay, we are imagining. A small h is nothing but we are divide. So what are the imagination we are going to implement in the future? Okay, in the future, small h1. I said no, like only some family cars. Which are okay, which we are going to implement in the future, like a driverless cars and etc. and etc. This all positive comes under, okay, this all positive and this all are the negative. Okay, this all positive and this all are the, this all positive and this all are the negative. So this all comes under the family cars and this all comes under the not a family cars. This is the target function we required, which is we have to find out in this mainly which is approximately correct. What is approximately correct? We required the family cars. So in the whole universe, we have different companies, different cars we have. In that, we have to do the prediction and we have to identify that which is belongs to a family car and which is not belongs to a family car. We have different companies, right? In that, we have to, the machine has to identify. Whenever we are asking a machine that show me the family cars and different companies with the prices and etc. and etc. So the machine will predict that and it will show that exactly which is the family car and which is not a family car. So, so here you can see this. This is the, okay, epsilon. So here C is the target function here, and HS is the hypothesis of that. And if the generated hypothesis does not touch any of this region, error region is greater than epsilon and not approximately correct because the error region got increased. So here you can see this in the next graphical representation. The error region is increasing. So how it is increased? So here you can see this. So already in the previous one, if you see this, in this we have only the less error region. So whenever we are going here, whenever we are not training the data sets with proper, the error region will be increased a lot. So here you can see this only we have one place here and all places comes outside. So this error region has been increased. So if there is no proper data set, so we are not training the machine with a proper data set, what happens? The error region will be increased more and more. So here you can find out that the plus only plus we have here, all the plus comes outside of this. So only it is showing only one car here. Example, only one car it is showing. It is not showing all cars. Previously we have yeah, all together it is showing this all comes under the family cars. So whenever the error region increase, it shows only one or two. Okay, it all comes under the outside. So this directly we can say that the error region has been increased. Okay. So here you can see this error region, sum of four rectangular strips. Okay, greater than epsilon. Each strip is at most. Okay, epsilon by 4. So what is epsilon by 4? Here we can find out that to finally we get, so to overcome this, finally we get epsilon by 4. Four sides we have epsilon by 4 to decrease the uh, error. To decrease the error, what we are doing, we are writing all epsilon by 4, epsilon by 4, epsilon by 4, epsilon by 4. So this is the target, C is the target function in this. Okay, so here you have to find out that in this mainly what is the target function given and what are the target functions we are going to implement. Okay, this all comes under this. So we have to show that whether the errors has been increased or decreased. Okay, whether it is approximately correct. Actually, what is our target here? Our target is to find out whether it is a family car or not. So here we are finding that it is a family car. Okay. Next, I am going with the other concept. So Bayes theorem. I want to discuss about the Bayes theorem. Before going to the Bayes theorem, here we have what is Bayes theorem. Bayes theorem is given by the English scientist, philosopher. Okay, he is known as a Mr. Thomas Bayes in the 17th century. Bayes provides their thoughts in decision through which is extensively used in important mathematics concept as probability based. Okay, Bayes theorem. So here, Bayes theorem is, here you can see in the definition that Bayes theorem is one of the most popular machine learning concepts that helps to calculate the probability of occurring one event with uncertain knowledge while other one has already occurred. So, uh, so in the machines, what we are doing here is some machines will predict the problem and directly it will identify that problem and directly it will show the results for us. Okay. Directly we are going to get an output for that. So here in the Bayes theorem, you can see that Bayes theorem is one of the most popular learning concept that helps to calculate the probability of occurring one event with uncertain knowledge while other has already occurred. Bayes theorem can be divided using product rule and conditional probability of event X with E known as Y. According to the product rule, we can express an probability of an event with X known as event Y. So here you can see this. We can say that the probability P of X by A equal to P of Y by X into P of X by P of Y. So here we can write not only this, we can write about P of A by B equal to P of B by A into P of A by P of B. Okay. So here we called it as P of X. What is P of X? So here we are going to discuss this is a formula for the Bayes theorem. Whatever the calculations we are doing in this theorem, it totally depends upon the Bayes. Okay, it totally depends upon the Bayes rules. So here we call it as, so here P of x by a, we call it as an posterior. A P of x, y by x, we call it as an likelihood. Okay, what is posterior? Posterior, it is called the, so why we call it, why we are calling this as a posterior? P of x by y, x by phi is a posterior which needs to calculate. It is used, it identifies and defines the updated probability after considering the evidence. Okay, whatever evidence are there, suppose if you want an output directly, if you are asking any query to the machine has, every time it has to be updated and it has to give the result for us. So here it is known as the posterior. P of x is called as posterior, which we need to calculate. I defined as updated the probability after considering the evidence. What are the evidence are there? Okay, that will be considered using updations. Okay, this we call it as an posterior. P of y by x is called as likelihood. It is the probability of evidence of hypothesis is true. So already I said this we have P of y by x. What is the y by x? It is an evidence of the hypothesis is true. So how we have to say that hypothesis is true? So here we are doing the, just we are doing the imagination in future. Uh, Example, in future we will have the robotic teacher that will be in future existing, right? So that comes under that. So we can say that it is a true. Okay, that in future we have existed. Previously there was no touch screen monitors, etc., and etc. But previously they have design, they have some plannings to implement the touch screens. Okay, so now they are in existing. So we, that is the imagination, and now it comes under the existing. Okay, we call it as an P of x is a likelihood. Likelihood is the probability of an evidence which, when hypothesis is true. P of x is called as prior probability. Prior probability is before considering the evidence. Okay, before considering the evidence, we call it as an prior probability. Okay, P of y is called the marginal probability. It is defined as a probability of an evidence under the consideration. Okay, so here we can say that hence Bayes theorem can be written as posterior equal to likelihood into prior by evidence. So here we can say P of x by y equal to P of y by x into P of a by P of x by P of y. Okay. If we take another example for this, P of a by b. So this is a posterior here. P of a by b is the posterior. So likelihood, what is likelihood here? P of b by a is the likelihood into P of a by P of b. P of b is nothing but the evidence of that. This is a prior. This is likelihood. So whenever you're writing about the Bayes theorem, this formula is very useful here. So what is here posterior? Posterior here you can say that P of x by y. X by y is called as an posterior. Okay, P of y. This is, and likelihood. Like what is likelihood here? Likelihood is P of y by x. What is prior? Prior is P of x. Evidence. Evidence is P of y. Prerequisites for a Bayes theorem. While studying the Bayes theorem, we need to understand few important concepts in this. First one, experiment. An experiment is defined as a planning operation carried out under under controlled conditions such as tossing a coin, drawing a card, and rolling a die. Okay, already this experiment we have like uh, if we have dice, we will throw the die. According to that, we are going to what, every time we will not get the same, okay, same number in the die. Okay, we'll get a different number. So that will do the prediction on that. Now, sample space. During an experiment, we will get a result is called possible outcomes, and set of the possible outcomes of an event known as sample space. For example, if you are rolling a die, sample space will be so here he took the example of rolling a die. Okay, we are rolling a die. One. We have total. We have, so one time we may get 1, 2, 3, 4. Okay, different numbers we are going to get. Where in the same, it almost every time we will not get the same number. Okay, whenever we are throwing a die, we will get a different number. When another time if we are throwing a die, we will get a different number. So different numbers we are going to get. So we call it as an S1 is equal to 1, comma 2, comma 3, comma 4, comma 5, comma 6. Similarly, when we are having a coin, okay, when we are tossing a coin. So here either there are two two possibilities are there here. Either we may get head or either we may get tail. Okay, two possibilities are there here. One is head, other is tail. Okay, event. Event is defined as the subset of the sample space in an experiment. So it is called the set of outcomes. So it is called a set of outcome. This is the event E, and this is the sample space S. Event E is called event is E, and the sample space is S. So assuming in an experiment of rolling a die, there are two events A and B such that A equal to event when an even number is obtained. So here we have an event. So in this, you can see that A is an event. So event is known as nothing but the even numbers in this. Okay, A is an even number in this, obtained even number. So here you can say that even numbers we have in the die. Whenever throwing the die, we may have even numbers of 2, 4, and 6. Okay, so here B, we are taking another one is B, is the event and the greater than 4. So we call it as a 5, 6. Greater than 4 is 5, 6 are there. So here the probability of the event P of A, number of favorable outcomes by total number. Okay. So here we have the possibilities of outcomes here. P of E equal to 3 by 6. Okay. 1 by 2 is equal to 0.5. So similarity, the probability of same we are going to take for the B. Okay. 2 by 6, 1 by 3, we will get 0.333. So here we have union. Okay, A union. So this is A and this is B. So this is the intersection here. So we are having the possibility of an event here. So you can say that B A union B. Here you will have this is A and this is B. Okay. So union of a event A and B, A union B, 2, 4, 5, 6. Okay. Next intersection of an event of A and B. So here we have an intersection here. Okay, A and B. This is the intersection here. Then this is the union and this is the intersection in this. So here in the this is the disjoint event. So here we have the intersection. This is the union and this is the intersection. Here you can see this. This is the union and this is the intersection. So in this you can see that the disjoint event, if the intersection of an event A and B an empty set null such that event known as disjoint event. Okay, this is not intersection. We don't have intersection here. We call it as a disjoint. Okay, disjoint event we call it as. So here it is event E and this is event F. So this is known as the disjoint event random variable if it is a real value function which helps mapping between sample space, okay, and a real line of experiment. A random variable takes and some of the random values, or each value having some probability is either random or not a variable, but it behaves as function which can either discrete, continuously, and combination of both. So here we have event F and event E and event F. We will take some random samples. According to that, we are going to implement in this, we call it as an random variable. Okay. So here in the exhaustive event, as per the name suggested as an event where at least one event occurs at a time called exhaustive event of an experiment. Two events A and B are said to be exhaustive if either A and B definitely occurs at time and both are mutually exclusive. Example, while tossing a coin, either it may be a head or tail. Okay. So here we may have two possibilities in this also. Here, whenever we are tossing a coin, okay, either we may get the positive, here we may get the head or tail. Okay, we have two possibilities. Whenever we are tossing a coin, we will get to either head or either tail. Okay, so we will predict that whether we may get to head or tail in this. So here we have an independent event. Two events are said to be independent when occurrence of an event does not affect. Okay, the occurrence of another event in simple word can say that the probability outcomes of an event depends on another one. Okay, P of A and A union B equal to P of A by B equal to P of A into P of B. So we have another one is conditional probability is defined as a probability of an event A. Give the number another event B has already occurred. this represents P of A by B, and we are defined that P of A equal to P of A and B by P of B. So here we have marginal probability. Marginal probability is defined as the probability of an occurrence independent of an event. Further, it considered the probability of an evidence under an consideration. What is an evidence? Whatever the outputs, what are the results we are going to get, that is an evidence for that. Okay. So here we have P and P and not B, P and A, B and P, B. So here so already you said maximum likelihood, it leads to square hypothesis in machine learning, both likelihood estimations and least squared error are common approximation used for hypothesis modeling and parameter estimation, but they are typical applied in the different context. So here you can see that what is already in the previously we have seen the how the error will occur. We have to whether it is a family car or not. So in the, wherever we find the positive, so positive is nothing but in the square bracket in the rectangular that will implements as that is a family car, and outside we have minus that comes under the not a family car. So here we are doing the prediction. If the error has been increased more, what happens? If the error has increased more, so there we will get only one plus we have seen in the graphical representation. So here we can find out that how we have to identify whether the error has been increased. We are not going to get proper and accurate results for that, accurate output for that. Whatever we require, example, if you are asking a machine that we require only the all companies family cars are required, so it will show only one or two. Why? Because we have not trained the machine. There has been the error has been increased more. So due to that, we are not getting the proper result. Okay. So maximum likelihood estimation. So LE is a method of used to estimate the parameters of the statistical model by maximizing the likelihood functions. It assumes that the observed data is generated for a probability distribution, and the goal is to find out the parameters that makes the observed data and the most likely. Okay.